Now, in this video, we take up chemical properties of alkyl halides. Chemical properties of aryl halides will be taken separately. Now, chemical properties of alkyl halides, they can be divided into four major categories. One is nucleophilic substitution reactions called NSRs. Second, elimination reactions. Third is reactions with metals. And fourth category of reactions will be some miscellaneous reactions. So we'll take up these reactions one by one. First category of reactions, NSRs, that is nucleophilic substitution reactions. For this, we should know what is a nucleophile. Nucleophile, first of all, the symbol for nucleophile is NU with two dots on U. Why these two dots? I'll tell you. This is based on definition. So nucleophile is an atom or a group of atoms which contains minimum one lone pair of electrons. These two dots represent lone pair of electrons in the nucleophile. So nucleophile may be an atom or a group of atoms which may be neutral or may be negatively charged, but it contains minimum one lone pair of electrons which it donates to the electron deficient center and forms a bond with it. Now, if we consider alkyl halides, carbon atom which carries halogen is called alpha carbon atoms. So this is alpha carbon. And you can see due to polar nature of the bond, alpha carbon is electron deficient. It carries partial positive charge. And due to this positive charge, electron rich particle, that is nucleophile. Nucleophile is nucleus loving. Nucleus loving means positive site loving particle. So nucleophile will attack alpha carbon atom which is electron deficient. Now, as per definition, nucleophile will give its lone pair of electrons to carbon and form a bond with it. Nucleophile has given lone pair of electrons and that lone pair has been used to form a bond with carbon. This bond between carbon and halogen will break heterolytically. Halogen will be eliminated as halide ion. And these three bonds will remain intact. These may be inverted like the umbrella in a storm, right? Nucleophile replaces halogen. That is why this type of reactions are called nucleophilic substitution reactions, because a substitution reaction has taken place with the help of a nucleophile. Now we take up different nucleophiles, we'll get different products. So we'll take up total 19 nucleophilic substitution reactions one by one. They'll be easy. The only thing is, if you understand them properly, it will not be difficult to write product. So that was the representation of any nucleophilic substitution reaction. You just replace halogen by the nucleophile. First nucleophilic substitution reaction is reaction with aqueous NaOH. Aqueous NaOH will ionize to give Na plus and OH minus ions. OH minus ions will act as nucleophiles. So oxygen of hydroxide ion will donate lone pair of electrons and form a bond with R. Halogen will be knocked out as X minus ion. This X minus will combine with Na plus to form NaX. The product obtained is an alcohol, right? So aqueous NaOH provides hydroxide ions. Hydroxide ions will act as nucleophiles. Nucleophile attacks alkyl halide, knocks out halogen, and takes its position. Product obtained is an alcohol. Second is reaction with sodium hydrogen sulfide. Oxygen and sulfur belong to same group of the periodic table. In place of oxygen, now it is sulfur. This is sodium hydrogen sulfide. Like NaOH, this will also ionize to provide SH minus ions. SH minus ions are called hydrogen sulfide ions. I'll repeat, hydrogen sulfide ions, or we also call them bisulfide ions. Product will be written in the similar manner. In place of oxygen, it is sulfur. The product is RSH and sodium halide. This is thioalcohol, also called mercaptan. So when alkyl halides are reacted with sodium hydrogen sulfide, product obtained is thioalcohol. Thioalcohols are also called mercaptans or also called thiols, right? That is the product formed. Third is reaction with water. Although we can think of water as H plus and OH minus, OH minus will act as nucleophile and product will be same as we got the product with aqueous NaOH, but will not use water in the form of H plus and OH minus ions. Why? In 11th standard, in the chapter of equilibrium, you studied about one topic, that is ionic product of water, Kw. Value of Kw is 10 raised to the power minus 14 mole square per liter square. On the basis of that topic, if you remember, concentration of H plus and OH minus ions in pure water is 10 raised to the power minus 7 mole per liter each. This very, very low concentration of ions in pure water shows that water ionizes to a very small, I should say, to a negligible extent. So in this reaction, we'll consider water as a neutral nucleophile. When water as neutral nucleophile attacks alkyl halide. See, I'll explain the way I did earlier. Out of two lone pairs of electrons at oxygen, one is used to form a bond with carbon. One lone pair is left. This carbon will carry, this oxygen will carry positive charge because it has given a lone pair of electrons. Halogen is knocked out as halide ion, X minus. Now remember, there's a difference when the nucleophile is negative and neutral. In case nucleophile is negatively charged, we simply knock out halogen and in place of that we write the nucleophile. But when the nucleophile is neutral, like in this case, it will attack, give lone pair of electrons, form a bond with alpha carbon atom, but at the same time, as it forms a bond with electron deficient carbon, at the same time, from the nucleophilic part, this is the nucleophilic part, from the nucleophilic part, a small positive ion will be eliminated. This is small positive ion H plus. This H plus later combines with X minus to form HX. These two electrons, they will be left with oxygen atom with a negative charge. This negative and this positive will become neutral. So I'll repeat, whether the nucleophile is negative or neutral, in both the cases, nucleophile will attack positively charged alpha carbon atom, give its lone pair of electrons to form a bond with alpha carbon. That is common in both the cases. But when the nucleophile is neutral, one thing additional will take place. When the nucleophile is neutral, then after formation of bond with alpha carbon atom, from the nucleophilic part, a small positive ion will be eliminated, and that positive ion will combine with X minus to give neutral product. So in this case, product form will be, first you think nucleophile forms a bond, it becomes ROH2. From OH2, small H plus will be eliminated. So ultimately product will be ROH, that is alcohol. H plus will combine with X minus to give HX. It means in nucleophilic, in NSR number 1 and 3, in both the cases, organic product formed the same, that is alcohol. But if you want to prepare alcohol from an alkyl halide, should we use reaction number 1 or reaction number 3? See, we'll use that reaction which is faster of the two. It should be controllable, no doubt, but should be faster. See, out of reaction number 1 and 3, reaction 1 is faster compared to reaction 3. Why? Because in case of reaction 1, nucleophile is negatively charged. And when nucleophile is negatively charged, it will be strongly attracted by positively charged alpha carbon atom, and therefore the reaction will be faster. Whereas in reaction number 3, nucleophile is neutral, and attraction of a neutral nucleophile with positively charged alpha carbon atom, attraction will be weaker, therefore attack will be slow, reaction will be slow, that is formation of alcohol will be a slow process. Now coming to reaction number 4. Fourth is reaction with ammonia. Ammonia will act as a neutral nucleophile. When it acts as a neutral nucleophile, nitrogen will form a bond because nitrogen carries lone pair of electrons. Initially it will be RNH3, but immediately from NH3, a small positive ion, that is H plus ion, will be eliminated. RNH2 will be left. H plus will combine with X minus to form HX. So product obtained is a primary amine. Reaction number 5, reaction with primary amines. This is primary amine. When primary amine attacks alkyl halide, bond will be formed through nitrogen because nitrogen carries lone pair of electrons. Now nitrogen is attached to 2 hydrogen atoms and 1 alkyl chain. Out of 2 hydrogen and alkyl, smaller part will be H plus. H plus will be eliminated, remaining 1 hydrogen and 1 alkyl will be left. So we get a secondary amine and HX. This is secondary amine form. Next, reaction number 6 is reaction with secondary amines. This is secondary amine. Again, attack will be through nitrogen. Nitrogen is bonded to hydrogen, alkyl and alkyl, hydrogen, alkyl and alkyl. After bond formation, there will be immediate loss of small H plus ion, which combines with X minus to form HX, and this product obtained is a tertiary amine. Last 3 reactions, that is reaction with ammonia, reaction with primary amine, reaction with secondary amine, that is reaction number 4, 5, and 6. Collectively, they are called Hoffman's ammonolysis. All of them are called Hoffman's ammonolysis. Next, NSR number 7. This is a reaction with aqueous sodium iodide or aqueous potassium iodide. They will ionize to give I minus as nucleophiles, will lead to the formation of Ri and Kx or NaX. If you remember, we have already studied this reaction. This reaction takes place in the presence of acetone. This halogen should be chlorine or bromine. If you remember, we studied this reaction under preparation of alkyl halides, and this is called Finkelstein's reaction. You can check Finkelstein's reaction. Next. Next is reaction with alcohols. Later in the next chapter of organic chemistry, you'll study that alcohols are acidic in nature. Acidic means alcohol will ionize to give RO minus ion and H plus ion. RO minus ion is called alkoxide ion. And this alkoxide ion will act as a nucleophile. Now, once you know the nucleophile, it is easy for you to write the product. It will attack R. Bond will be formed through oxygen. H plus will combine with X minus to form HX. ROR dash. Product is an ether. But this reaction for the formation of an ether is a slow reaction. Why it is a slow reaction? Because alcohols are weak acids. Weak acids means ionization of alcohol to generate alkoxide ion. That is a slow process. Since nucleophile is generated slowly, it means the reaction is slow. Formation of ether is a slow process. Now, this reaction will be fast if generation of alkoxide ion, generation of nucleophile somehow becomes fast. So, ninth property is reaction with sodium alkoxide. Sodium alkoxide means sodium salt of alcohol. This is sodium alkoxide. This is an ionic compound. This will easily ionize to generate alkoxide ion and sodium ion. Nucleophile is same. Product will be same. Byproduct will change. This will be NEX, sodium halide. So, sodium alkoxide is ionic compound. Therefore, it ionizes very easily. Generation of nucleophile, that is alkoxide ion, is fast. Therefore, this is a fast reaction for the preparation of an ether. So again, if we want to prepare an ether, we'll not use reaction number 8. We'll use reaction number 9 for the preparation of an ether. And this method, this reaction is called Williamson's synthesis. Now, similar to reaction number 8 and 9 are reaction number 10 and 11 respectively. In reaction number 8, we reacted alkyl halide with alcohol. Now we'll react with R-SH. What is this? Mercaptan, thioalcohol. This will ionize to give RS minus ion. RS minus ion is called mercaptide ion. So this is reaction of alkyl halide with a mercaptan, that is thioalcohol. Thioalcohol will ionize to give mercaptide ion and H plus. Mercaptide ion will attack like alkoxide ion and will lead to the formation of this is similar to ether. This is called thioether plus HX. Like reaction number 8, this reaction number 10 is also a slow reaction, and the reason is same as for reaction number 8. What was the reason? It's a weak acid. This is a weak acid. Ionization is slow. Generation of nucleophile is slow, and therefore reaction is very slow reaction. Next, 11th reaction, we take salt of thioalcohol, that is sodium mercaptide. Salt of mercaptan is called sodium mercaptide. So 11th property is reaction with sodium mercaptide. This is ionic compound. This will easily ionize to generate the same nucleophile and sodium ion. Organic product will be same, that is thioether. Byproduct will change. This byproduct will now be NEX. This is a fast reaction. Reason is same as the reason in NSR number 9. Again, if you want to prepare a thioether, we'll use reaction number 11, not reaction number 10. 10 can be used, but that's a very slow reaction. Next, reaction number 12. This is the reaction with sodium sulfide Na2S. This will ionize to give 2 sodium ions and 1 sulfide ion, which carries -2 charge. When this nucleophile attacks, when -2 charge enters, it means -2 charge should come out. This is the reason 2 halogen atoms will be knocked out, for which 2 alkyl halide molecules are used. Product obtained will be RSR plus 2NEX. In this case also thioether is obtained, but this thioether will always be a symmetrical thioether. Means both R's, both alkyl chains should be same. Next. Number 13. Reaction number 13 is reaction with potassium cyanide or sodium cyanide. Sodium or potassium cyanide, these are ionic compound, will give Na plus and Cn minus ions. This will act as a nucleophile. Now, there is something very important which I'm explaining now. This nucleophile. In this case, carbon as well as nitrogen, both atoms carry a lone pair of electrons. And as I told you, attack will take place through that atom which carries lone pair. If nucleophile attacks through carbon, product will be RCN, cyanide. And if attack takes place through nitrogen, product will be RNC. RNC are called isonitriles, isocyanides. And both are very well known compounds. So through which atom will attack take place? How do we decide that? I'm writing 2 resonating structures for this nucleophile. Now you can see carbon as well as nitrogen both carry lone pair of electrons. Both carry negative charge as well. Negative charge. Now, in this case, attack will take place through carbon but not nitrogen. Product will be RCN. But why will the attack take place through carbon? Why not through nitrogen? The reason is carbon is less electronegative than nitrogen. What is nucleophile doing in these reactions? Nucleophile is giving lone pair of electrons for bond formation. that atom will give lone pair of electrons more easily, which is less electronegative. Since carbon is less electronegative, donation of lone pair of electrons will take place through carbon, not nitrogen, and product obtained is RCN, not RNC. Product is nitrile. Next is reaction with silver cyanide. Silver cyanide is a covalent compound. It does not ionize. Lone pair is present at nitrogen only. Therefore, attack has to take place through nitrogen. After bond formation from this neutral nucleophile, silver is lost as Ag plus ion. That Ag plus combines with silver X minus to form AgX. The product obtained in this case is isonitrile. So be careful when the reaction is carried out with sodium or potassium cyanide, product is RCN, nitrile. If the reaction is carried out with silver cyanide, product obtained is isonitrile, that is isocyanide. Next. Reaction with KNO2. This ionic compound will ionize to give K plus and NO2 minus. NO2 minus will be nucleophile. I'm writing two resonating structures of nitrite ion. You can see both are equivalent resonating structures. If you flip one structure like this, you get the second structure. Both are equivalent resonating structures. All atoms carry lone pair of electrons. Attack will take place through which of the three atoms? Attack will take place through oxygen. Although oxygen is more electronegative, attack will take place through negatively charged oxygen, because negatively charged oxygen is less electronegative than neutral nitrogen. Nitrogen is neutral in both resonating structures. Attack will not take place through neutral oxygen. Neutral oxygen is more electronegative than nitrogen, but negative oxygen is less electronegative than nitrogen. Therefore, attack will take place through this negatively charged oxygen and will lead to the formation of RONO. This is alkyl nitrite. Product obtained is alkyl nitrite. Next is reaction with silver nitrite. Silver nitrite is a covalent compound. It does not ionize. This is AgONO. This is the neutral nucleophile. No charge on any atom. Now, in this case, it's a neutral nucleophile. In this case, attack will take place through nitrogen, because neutral nitrogen is less electronegative than a neutral oxygen atom. So attack takes place through nitrogen. Silver is lost as Ag plus, combines with silver halide to form AgX. Product is nitroalkane. Nitroalkane is obtained. Three more NSRs. Number 17 is reaction with sodium carboxylate or silver carboxylate, means sodium salt or silver salt of carboxylic acid. Silver or sodium carboxylate is ionic compound. This will ionize to give metal ion and carboxylate ion. Carboxylate ion has two equivalent resonating structures. This is one, and the second is RCO, and this is double bond. In this case, attack will take place through negatively charged oxygen atom. Wait a minute. Negative. Attack will take place through attack will take place through negatively charged oxygen atom. This R will form a bond with negative oxygen. Product formed is an ester. Esters are sweet smelling compounds. Ester is obtained, but you have to be very careful in writing structure of the ester. There are two alkyl chains, R and R dash. Alkyl group attached to the oxygen atom that comes from alkyl halide. Alkyl chain attached to carbon atom that comes from sodium or silver carboxylate. That you have to be very careful. Next is reaction with sodium alkynide. It means sodium salt of alkyne. This is the nucleophile called alkynide ion. Ethynide, propionide, butynide will be the nucleophile. This carbon will form a bond with this alkyl chain. We get an alkyne with more number of carbon atoms. That is, we get a higher alkyne. Next, and the last NSR. Next is reaction with LiAlH4. LiAlH4 is lithium aluminium hydride. It ionizes to give H minus ions. I hope you remember H minus ions are called hydride ions. So lithium aluminium hydride gives hydride ions as nucleophiles. Hydride ions combine with R to form alkane plus LiX plus AlH3. The product obtained is an alkane, and this is called reduction. This reaction is called reduction. Two very small topics related to these 19 NSRs. One is ambident nucleophile. Ambident nucleophile or ambident group. If you remember, I told you about CN. CN can form a bond through carbon or can form a bond through nitrogen. So those groups of atoms which can form a bond with alkyl chain through two different atoms, they are called ambident groups or ambident nucleophiles. we came across two ambident nucleophiles in these NSRs. One was CN and C, the other was NO2 and ONO. These are ambident nucleophiles. One more small topic about reactivity of alkyl halides in NSRs. In all these NSRs, bond between carbon and halogen is to be broken. If the bond is weak, it will break easily. Breaks easily means reactivity of alkyl halide is more. When is the bond weak? When bond length is more. Bond length increases as we move down the group. Atomic size of halogen increases. Bond length increases. Bond becomes weaker and breaks easily. And that's why reactivity of alkyl halides will also increase. This is the reason reactivity of fluoroalkanes is least, followed by chloroalkanes. More reactive than this will be bromo, and iodoalkanes have maximum reactivity in nucleophilic substitution reactions. There are many more topics related to NSRs like mechanism and stereochemistry that we'll take up in subsequent videos. Right? That's all about today's video.